We're going to look at motion in a vertical circle, but we're going to look at how speed affects it. Specifically, I'm interested in why you can spin something over your head, or why you can be in a roller coaster and go around a vertical loop and be on the inside, right? Your cart's here and it travels around this loop, comes around on the inside. You're sitting right here. Why don't you fall out? Why can you spin something vertically and not have it fall from the top? Why is that allowed? Well, if you think about the case where it's at rest, then there's only one force acting, and that force is gravity. And if that was the case, then you would plunge and plummet, and that would be bad. Okay? But that's not what's actually happening. We're actually accelerating around the circle. We have motion this direction, which means this force is required to keep us moving in a circle. We have that force towards the center. There is a centripetal force, right? The net force is our centripetal force. It's causing us to move in a circle. And if you think about that, when we're moving, if we're right here, when we're going this way, we want to keep going that way because of our inertia, and we want to continue moving in a straight line. So the track actually exerts a force in on us towards the center of the circle that keeps us moving in a circle. And when we're right at the top, the gravitational force and the track's force act together. So the track doesn't have to push as hard, but it does still have to push. So let's take a look at that. What we're saying is you're going to fall out if the track isn't pushing on you, because then the only force that's acting is gravity. But if the track is pushing on you, then you're going to be okay. And remember, the force that a surface exerts on an object is called the normal force. So what we're saying is the normal force needs to be greater than 0. If that's the case, then the net force, which is the centripetal force, is actually caused by two forces. We have Fg, the force due to gravity pulling down, plus Fn, the normal force exerted by the track, also down. That equals Fc. Okay? Now I'm going to go ahead and I'm going to solve this for Fn. So I have the normal force is equal to Fc minus Fg. But remember, I said up here, if we're not going to fall out, then the normal force has to be greater than 0. So this whole thing is greater than, not greater than Fn, that whole thing is greater than 0. Now let's take a look at what that means. I think we have enough information to find the minimum speed of which we can go around this track. Okay? And I said over here that I had a radius of 5 meters, but I'm going to change that. I'm going to change that to a radius of r meters, a speed I don't know, and a mass of m kilograms. So let's see this thing going around the track and see if we can figure out its minimum safe speed. Okay, so I have Fc minus Fg has to be greater than 0 if we're not going to fall out of our track. That is to say, the centripetal force is greater than the force due to gravity. That makes sense. If it takes more force to push us in a circle than gravity can provide, then we're not going to fall out of our seat. However, if gravity can provide more than enough force to keep us moving in a circle, then we're going to accelerate more than our centripetal acceleration, and we're going to fall out. That's just not a good day. All right, so Fc is greater than Fg. Well, remember, Fc is m times centripetal acceleration, which is greater than Fg, which is m times the acceleration due to gravity. Well, that's m on both sides, so it doesn't matter what your mass is, it cancels out. AC is v squared over r, and this has to be greater than g. Okay? All right, well, this lets me see that my safe velocity v has to be, or v squared, sorry, has to be greater than g times r, and that I can summarize nicely with v has to be greater than the square root of g times r. If v is less than the square root of g times r, then we're not going to have enough force, or the force due to gravity is going to be greater than the centripetal force, and we're going to fall out of our chair. Okay? So if this did have a radius of 5 meters, then we could say, oh, well, 5 times 9.8 is 49, and the square root of 49 is 7. So we would know we have to navigate, we have to be going at least 7 meters per second at the top of this circle so that we don't fall out of our roller coaster. Just like there's a minimum safe speed for going around the top of a loop, there's also a maximum safe speed for going over a bump or over a loop. Okay, so if you think about this, think about a road where it's, for the most part, fairly straight, but then there's a hill in it. Okay, or something like that. Now, there's some interesting analysis we could do here. Where's the normal force? Where are you going to feel the heaviest? Where are you going to feel the lightest? But for now, I want to think about this spot right here. When you're at this spot right here, your car wants to keep going straight. And the reason it wants to keep going straight is because it has inertia. Inertia is a tendency to resist a change in motion. However, the road drops down below you. If there was no gravity, you would keep going straight. But there is gravity, and that gravity pulls you down. That gravity causes you to stay on the road. That is, it's accelerating you in a circle. Okay, so the center of my circle is here, and we're getting accelerated that way. However, that's not the only force. Because you're sitting on the road is pushing up on you. Now, if you go over this corner too fast, you can actually jump and launch yourself off the road, right? We've all seen that in movies. We've seen motorcycles do that. So I want to know, what's the maximum speed you can navigate this hill and still actually stay on the road? Now, remember, in a centripetal motion problem, we generally say towards the center is positive, and my center is actually down here. So this way is positive. So again, I'm going to be looking at the net force. The net force is still mass times acceleration, but it's centripetal acceleration because we're only accelerating in a circle. So that is, the net force is centripetal force. So I have Fc is equal to Fg minus Fn. Okay? And the reason I'm subtracting Fn is because it's negative compared to Fc and Fg, because positive is down. Now, if we're actually going to navigate this safely, that means we want our tires to be in contact with the ground at all time, which means we want our normal force to be greater than 0. So this is a lot like what we did before. We have our normal force greater than 0. So I'm going to go ahead and I'm going to solve this for the normal force. So I'm going to add the normal force to the left, and I'm going to subtract Fc over, and so I get the normal force is equal to Fg minus Fc, and so that means Fg minus Fc has to be greater than 0 since our normal force is greater than 0. So if we just carry this through a little bit, Fg is greater than Fc. Gravity provides more force than is required for the centripetal force, so we need the normal force to balance it. If gravity is less than Fc, then you don't have enough force to actually turn this circle, and you're going to fly out of this. So now, if the car has mass m, and the curve has radius r, what is the speed v that you can navigate the hill with? Well, Fg is mg, and that has to be greater than mv squared over r. Mass is on both sides, it goes away, so g times r is greater than v squared, right? Multiply both sides by r, so again, square root both sides, and I get a result that's similar to the one I had before. I get the square root of gr is greater than v. Okay? So this is actually a lot like our last example, but exactly the opposite. Here we had v is greater than the square root of gr, and on the other side of the hill we have gr, the square root of gr is greater than v.